We're trying out ShiftScan. Today we'll be exploring how to run ShiftScan using a Google Colab notebook. The first thing you're going to want to do is navigate to the ShiftScan GitHub repo. The link is in the manuscript. However, you can just go to www.github.com/samshay42, that's me, /ShiftScan, and enter. That'll take you to the repo. We're going to scroll down here to the Colab option, and as it says, the link to the Colab notebook is here. We're going to click on that link, and that will open up the notebook. Now what you're going to want to do is copy this to your Google Drive so you can play with it. So you just hit or click this button that says copy to drive, and that's going to copy it into your Google Drive. It opens it up automatically. Here we can see copy of ShiftScan. I'm just going to close all of these just to show you where it is. So if I open that, I'm just going to close those down. We can go to our Google Apps. We click on Drive, and you should see a new folder called Colab Notebooks. You'll obviously have your other files and folders here, but this should probably be newly created unless you have other Colab notebooks. We double click on that to get in there, and you'll see your copy of ShiftScan. You can absolutely rename this to get rid of that copy of. It won't change the functionality, obviously. Anyway, let's get this running. So we open this up, and that will open up our Colab instance. Now I'm also just going to open these files so that you can see what's going on. I need an FYI here of sorts, I guess, which this sample data has absolutely nothing to do with ShiftScan. It's generated by Google each time you open up a Colab notebook. The purpose of it is basically so that if you're developing a new notebook or developing new code, you have some data to play with. I've written this last line here. It gets rid of that sample data, so please just ignore it. It has nothing to do with ShiftScan. Anyway, the first thing you're going to want to do is make sure that everything is running correctly. Well, get ShiftScan installed and running, and you run it with the example data. So we're going to do that, and I will talk you through what it's doing. So we go to Runtime, and you click Run All. So the first thing it does is it copies all of those files or clones those files from the GitHub repo. The next thing it does is that it installs any of the dependencies that ShiftScan needs, as well as this Jupyter Dash, which is just needed for this Colab instance. This can take a minute, and it's going to throw a little error here, and it's not going to be a problem. Let's just wait for it. There we go. Basically what it's telling you is that one of the packages that ShiftScan needs is clashing with all of these. We are not worried about this because ShiftScan doesn't use any of those packages, and it only exists in this little instance. So we can confidently ignore that. The next thing it does is actually runs the main ShiftScan script using the example input as the raw data, the example metadata as the metadata, and then it generates this example output folder, which I can show you. So we follow it, ShiftScan scripts, and then we'll see them. So ShiftScan scripts, and there they are at the moment. That's the input. Let's see, output should be empty because it's still running. There's several different messages that pop up and let you know what's happening. This is, Google Colab is a public enterprise, I guess, and so the speed can be quite variable of how fast these the data is processed. This is just 4 files, and as you can see, it's fairly quick, and it just basically depends on the traffic that Colab is experiencing. The next step is that basically we say, hey, we want to visualize this. Here's where the output from the main algorithm is. It fires up the app, and then this line runs the app, and then we had that other piece down here that gets rid of that sample data folder. This is the ShiftScan viewer, which is basically just a little visualization of our output. We can hit plate overview. We can see one of our plates failed with 9 controls failing, and the others were fine. We can go to the controls, and here we can see, so that plate, basically a whole bunch of these. This is the distribution of the melting temperatures in the controls before and after those outliers are removed. And we can definitely see that big blob of melting temperatures has been removed, which is probably why it failed. Additionally, we can look at the curves themselves and see, oh, why did you fail? And you can absolutely get rid not get rid of, but you can change the parameters to see which control curves are allowed to fail, etc., etc., etc. You can play with the parameters as much as you like. This melting temp overview is just a plate view of your results. You can either visualize it by melting temperature or color it by melting temperature, or you can do it by z-score, entirely up to you. I prefer melting temperature. It's just a personal preference. I think it's prettier. So scroll down here. And here you can click on your different wells to have a look at the individual curves. You can also look at some of the failed ones and see why they failed. You can keep scrolling for all of our different let's see, there we go, another failed one. And then obviously the business end of this is the hit list. This is a default hit list that is generated, whether it's the example data or your data, and it's based on the z-score distribution, which is described in our manuscript. However, if you want, you can go with the more traditional number of standard deviations. So here the default is 3, but you can change that to whatever you want, or a number of degrees from your control melting temperatures, or your average control melting temperatures. You can go with that. We'll leave it at 2. That's fine. Let's pretend we only want 0.25. We're going to allow that as our lower cutoff. So basically anything lower than a quarter of our control amplitude needs to be thrown away. Everything above is fine. And I'm going to say only stabilizers, hit update, and we have 21 hits. Beyond that, we can also investigate our individual hits by clicking on whichever row we like. The original curve will show up, as well as the first derivative. The red line is the average melting temperature for the controls on that plate, and the blue is for that specific well. If you decide, this is actually a really ugly curve, I don't accept it as a hit, you can click this little red cross and it gets rid of it. Additionally, you can also sort your data however you like, which is fine. And you can also look at all of the curves for your hits. I think it maxed, if I remember right, I maxed it out at 50. You're allowed to see 50 curves at a time. You can also see the summary graphs, and this is basically distribution of your hits in each plate. And this visualization really is only useful when you have fractions. So for example, we can see in plate 2 that most of the hits came from fraction 4, and this is the inverse, basically the fractions per plate. And so when you're done and you decide, hey, this is it, this is my hit list, you can click on export, and it will take export your hit list to a Excel file. Additionally, if you want to keep these raw files, you can go ahead and click over here, say download, and that will download to your personal, your local file system. Anyway, so this is all fine and dandy, but I'm sure you would like to analyze your own data. So let's just close this up. What we're going to do is we're going to go to runtime, and we're going to say restart the session, and so we click that. And we say yes. Basically, we want to clear it completely, so it's forgotten nearly everything. And then personally, I like to go to edit and clear all outputs just to neaten things up. And so we're sort of back at square one. Technically, we don't need to run the first 2 lines because ShiftScan in this session has been installed and the dependencies in this session have been installed, but you will need to run these every time you start a new session. And if you want, you can absolutely just default to running them all. It will not hurt anything. We'll see in a minute. It basically just says, I'm already installed, moving on. So what we're going to want to do our own data is we're going to right click and say a new folder. We're going to create something, we'll just call it my data. Oh, let's make that an underscore, that's ugly. There we go. And then we can right click on my data, and we're going to create a new 2 new folders actually. We're going to call one raw data, which is where we're going to put our fluorescence files, and the other one, oh no, we don't want to rename it, we want to new folder, there we go, and we're going to call this metadata. If I can spell it right. There we go. All right. And so now we can put our data from our local file system into here. So for the raw data, we right click and we say upload, and we can go to our raw files and we just select all of those and open. Basically, this warning is saying that, once you close the notebook, this data is not saved in the notebook, which is fine. You have your files on your local drive system, wherever it's saved. Just know that once you upload them, they're not saved forever. So you say OK. And then we can also upload our metadata. So you right click, say upload, and we're going to pick our metadata table, open. All right, so now we have all of our input data. What we're going to want to change is in these two cell code or cell blocks here. The first line we leave as is because that's running the algorithm, but the input we want to change, so we can just there and backspace. Content is basically the instance that we're working in, and here it's my data slash, what did we call it, raw data. That's where to find our input. The metadata, we're going to same thing, we're going to change that to match our own data. So we say my data is the folder. We're going to look in the metadata folder at the metadata, what did I call it? Table.txt, oopsie, wow, .txt. And then finally, we can store our output, let's say my data, which is the folder, and we're going to call it, let's call it demo output. You can call it whatever you want. And then finally, this input directory has to be this output. Basically, it's for the visualization. You're saying, hey, visualization, or ShiftScan viewer, here is the output from the main algorithm. Sweet guys, I'm not a robot. Don't know where that came from. Anyway, so just whoop. So this is running the main algorithm, and this is telling the visualization where to find the output from that one, so they can create the visualization. And that's all you need to change. And so we can go back up to runtime and hit run all. Again, it's going to say fatal blah blah. Don't worry about it. It hasn't broken anything. It's basically saying I already have ShiftScan. It does nothing. Same thing here. Technically, it'll run, but it'll say, oh, I have all of these. I'm not worried. And now it's going to run the main algorithm. So what it does is it runs the main algorithm using your new data here as the input, using the metadata as the metadata input, and then it creates the demo output folder. As you can see, it's empty right now. And as it, now it's processing, and when it's done, the output will be written to this folder. This is 8 plates worth of data, so it's going to take a little longer than the example data. It's shouldn't take too long though. I haven't done extensive benchmarking, but it seems to be fairly quick. Just a note, however, is that the free tier of Google Colab allows, I think it's 10 or 12 gigs of RAM. So using just the default algorithm, you can analyze 10 to 12 plates at a time. If you want to analyze more than that, I would recommend then either switching to the plate-wise version or the disk intensive version. It will take a bit longer, but you can do more. Or if if you have the resources, you can pay for the upgraded RAM in the Colab. I don't know what to call it, not network, but in Colab, the subscription. Or if you have hundreds and hundreds of plates, I would strongly suggest looking into using the command line version of ShiftScan in perhaps like a cluster environment. Again, it depends on your resources, and a lot of this is explained in the manuscript. Anyway, there's our 8 plates. They've been processed and ended. Now we're just comparing controls to experimentals. It's writing those output files, so they should show up any minute now. And there they are. There's the 4 output files. We're now using that as the input for our visualization. Basically, it goes to this output. It spins up the app and then runs the app. And now we have the results for all 8 of our own data, and we can go through the exact same steps that I described before to look at the data and inspect it and just decide what our hits are at the end of the day. When you're done and you've exported your hit list and you've saved your output files or whatever you've wanted to do, you can simply go to runtime and you just say disconnect and delete. Now that will get rid of everything. Yes. And from that point, you can just close it and you're done. And you can go straight into there the next time, and you'll see that those folders no longer exist, and you can start fresh. I hope that's been helpful, and good luck in finding all those hits and amazing compounds in the future.